All right, good morning, good afternoon, everybody. This is Brad Heers. I'm the Director of Structures Enablement within Simulia Dassault Systems, and this is our monthly Abacus update. This happens the fourth Wednesday of the month at 5 o'clock Central European Standard Time, and depending on time of year and so on, that could be anywhere between, I think, 8 a.m. and noon within the United States, and of course, any number of hours across the rest. So thank you all for attending. I appreciate especially those who are staying late to attend. We hope that this will be as useful and beneficial to you as some of the others have been. For those who have not been attending these regularly, they're fairly new occurrence, but our intent is to speak to existing Abacus users and knowledgeable customers and perhaps give some insight into tips, tricks, tools, and new features which perhaps are not available and known to many people. This is a bit of a catch-all thing. What our hope is every hour that we have this on each month is to have you leave a little more informed and perhaps happy you spent an hour learning a couple tips and tricks. And in that regard, I've got one that certainly fits the bill today. Austin Cox is going to be speaking about specialized tools to manipulate output data in Abacus. As many of you may already be aware, we've got a number of features in general for plugins and such that allow Abacus users to do a number of operations within Abacus CAE, within Viewer, even within the databases themselves. And many people are familiar with these, but maybe aren't familiar with some of the details. And in particular, Austin and his team have created a number of features that really do some very nice stuff in manipulating data, and anybody working in structural analysis over the last several years certainly knows that data just keeps getting larger. There's no limit or throttling down of ever-growing data sizes, and sometimes that becomes quite problematic in just simply managing the sheer volume. We've got a number of tools that have been developed that Austin is going to speak through, and I hope at the end of this you'll see where one can utilize a lot of these tools to maybe make your life a little bit easier, to cut down on storage space, to make runs easier to manage on smaller platforms. So with that, I will give you Austin. Take it away. As I recall, I think Austin's already given a little bit of an update on who he is, so I'll let him speak to that. Austin, it's all yours. Thank you.
Thanks, Brett. And just a quick mic check before I begin.
Sounds good.
All right. I'd rather do it now than 10 minutes from now. So thank you very much for that introduction. Just real quick before we begin, I see a couple familiar names in there. So I just want to say hi real quick to a couple of people I used to work with, Steve and Fabrizio. And I've got two managers, one previous and one current on here. So hi, Nuno. Hi, Dinesh. And that will take care of all of my highs at the beginning. So just wanted to say hi to a few people. So today we're going to be talking about Abacus database tools. We're going to be talking about a number of them, and we'll talk a little bit about how to manipulate them using the API as well, but primarily we're going to be focused on kind of prepackaged tools. And that's tools to do a number of different things, whether it's to convert databases, build them up, break them down, but we'll be talking about a number of different methods of kind of changing the shape of your databases. So just a brief background about myself. My name is Austin Cox. I'm a Simulia industry process consultant. I have a master's in aerospace engineering from Texas A&M University back in 2015, and I believe a few people from there may be joining as well, so hi to them if they have joined. I joined Simulia right out of university in 2015. A&D customer on-site support 2016 through 2019, and high-tech consultant over the last couple of years. I've taught a number of Abacus courses. If you can see the image on the bottom left, that is, again, back at Texas A&M, where I was teaching.
Austin?
Yes?
It does not seem to be advancing the slide.
Okay.
I'm still seeing your initial slide. There we are. Okay.
I think that'll fix it. All right. Thank you. So, yeah, high-tech consultant last couple of years. The image on the bottom left is just a seminar that I gave to some other students where I was teaching them. And did some rocket design. We had a day called Hug an Airplane Day, so that's me hugging an airplane. I like to take stuff literally sometimes. And, you know, if you see a Red Baron toy, you got to play with the Red Baron toy. But My general experience is in high-tech, aerospace, and defense, the two core industries that I've worked in. I've also got a bit of experience in transportation and energy, working with some people there. Expertise, Abacus, a simulation on 3D Experience platform. We'll talk about that briefly. Abacus, ODB, SIM database APIs, dabbled and worked extensively in a number of different languages, Python, Fortran, C++, JavaScript, Node, HTML. And just a quick snippet of some Abacus contributions. Multiple nonlinear load cases came out earlier this year. That allows you to skip some of the pre-processing if you're looking at nonlinear load cases. Some people are familiar with linear load cases, but that is now in there for nonlinear. Shear 4 elements, which was an aerospace requirement for an element type. OBT/ORB, which we'll talk about during this presentation, and a number of bug fixes. It's just a brief background about myself. So the first thing I want to talk about before we dig too deeply, Simulia has two database formats that are primarily used today. That's the ODB and the SIM database. ODB is the result format that's used with Viewer or CAE that most of you are probably familiar with. We have a newer database type that's called the SIM database, which is used in the Physics Results Explorer app on the platform. It's not used in Abacus CAE or Viewer, and as far as I'm aware, there's no current plans to implement that in CAE or Viewer. However, that's a new database. It's been out for more than 5 years at this point. Generally, when you're post-processing on that database and the platform, you have more capabilities than you do in Viewer. It's faster than it is in Viewer, but at this point, we don't have all of the original functionality covered, although we do have a large portion of it. And people that use that or want to go to the platform and use that, we kind of evaluate that on a case-by-case basis just to make sure that we have all the features that they want. But that database type, it works really well for very large databases. It includes aspects of HDF5, and it's built to handle these really large files. So if you look at the progression kind of through the years of databases, we started out with the .fil file, which is primarily Fortran based. We moved over to ODB, which is essentially the current standard, and that has C++ and Python, and we're moving over to SIM, which is going to be C++ and Python as well. Today's focus is going to be more on ODBs, since most of the tools today use ODBs. Again, I said we're eventually, we're migrating to SIM, and we're a good chunk of the way there at this point, but the current standard, I would say, is probably still ODB. That's where I see most of the usage today. So that's where we're going to focus. We've got a number of pre-made tools available for ODB. We don't have quite as many for SIM, but we do expect more in the future. So just to give you an example of time comparison for ODB versus SIM. So this is a large high-tech model where I've just taken it, done an initial load, and run through an animation. So loaded all of the displacement frames, loaded all of the strain frames, and the green is a showing of how long it takes the ODB to run through all of those frames, and the oranges are showing how long it takes the SIM database to run through all of those frames to produce an animation. So you can see that we have the ability to multi-thread, to do multi-core on SIM databases, and even without that multi-core, it's much, much faster than the ODB because of the architecture of the database. So if you're working with very large models, that might be an indication, if you're running into these very long times, that maybe the platform might be something to be interested in. Documentation exists for both ODBs and SIMs. It's available at that link. You have APIs for ODB and SIM, where the ODB API is generally richer in model data. It has all of the material sections profiles, where the SIM database may not have that. It's on the documentation. If you go to that website, you'll see the bottom image below. If you click User Assistance, it'll take you over to a page where you can navigate to the ODB's API, and you can look at the scripting reference there to look at the API. And then if you hit the Developer Assistance on the bottom right there, that'll take you over eventually to the SIM databases. With the pre-made tools that we have available, we also, again, have the APIs like we're talking about here. And the APIs make it really easy to read and write fields into those databases. So if I've got something pulled up in Viewer, for instance, and I'm taking a look at my stress output, all of that data is accessible through the API, and you can access the stress at the integration points. You can reposition them to be at the element nodes, and you can do a number of different things in the API, a lot of which you can do in the graphical interface, but not all of them. And you can do, very specific manipulations, and you can, toss in new databases, new fields to databases. You can, as we'll see later, reconstruct entirely new databases from data as well. But if you wanted to dig into, say, field outputs in the API, for instance, you dig into odb.steps.frames.field outputs. And then once you're in field outputs, the actual field output values would either be in .values or in .bulk data blocks. Now in .values, that's going to be slower to access, but you're accessing value by value by value. Bulk data blocks, it aggregates these into much larger arrays, and those are wrapped into what's called a bulk data block. So instead of going one by one with a class structure, which can be slow, you'd be doing array access, which can be an order of magnitude faster. So if you're looking for speeds and you're looking at ODBs and you just want to do your own manipulation, I would recommend looking into the bulk data blocks. And a few years ago, we put in an improvement to make them about 3 times as fast, thanks to actually some work that I was doing. So definitely worth your time if you're looking at going through the API itself. Now, an overview of tools that are available to manipulate output databases. We have split it into 3 categories, the first being converters. Converters includes Abacus ODB to SIM, to output 2, and upgrade. These are all command line commands. Combiners, we have the Combine ODBs tool, which is a built-in plugin. And built-in means that it comes shipped with the Abacus download whenever you download software. We have Abacus Restart Join, which is on the command line, and we have Abacus Substructure Combine, which is on the command line. We also have a number of reducers to break databases down. We have an ODB reduction tool, which is the ODB splitter plugin. We have the ODB reconstruction tool, which is command line based, available on the SLC, Simulia Learning Community. And we have the ORB, which is changed its name recently from OABT to ORB, which is my own tool that I've developed over the last couple of years. And that's available on the Simulia Learning Community at the moment, and in the near future, we expect it to be built in. That should be before too long. So additionally, again, as I mentioned, you have tools available in the user interface that allow you to manipulate the field output. So for instance, if I go into my output database and I open that up in Viewer, I can go to Tools, Field Output, and I can create new fields from previous fields. I can create fields from frames, and then I have the option to save those fields in the database whenever I'm finished. As far as the converter command line tools go, that first section, we have Abacus ODB to SIM, which allows you to convert an ODB file to a SIM database file. It allows you to visualize that post-processing data on the 3DEXPERIENCE platform. And again, that SIM database file is the one that's more HDF5 focused, that's able to handle much larger databases. And the SIM file is also used for some specific Abacus Salt processes, but it's not used at all for post-processing in Viewer. Abacus 2 Output 2. 2 Output 2 allows you to translate basic static or frequency results to OP2 files. If you're working with some other software that you need to convert to and look it up, you can do that. We have Abacus Upgrade as well. And Abacus Upgrade just takes an output database file from a current installed release to another current installed release. So if you have 2018 on your computer and you have 2020 on your computer and you want to use 2020, but the database is from 2018, you can use Abacus Upgrade to upgrade the database up to the current version. Now for combiners, we have the Combine ODBs, which is a built-in plugin that's available under Plugins, Tools, Combine ODBs. The basic uses for it are to combine output from different substructures in the same model. It allows you to combine output from 2 different analyses products as well, such as standard and explicit as part of a co-simulation. The good side, so the upside of combined ODBs is that it allows you to combine data from different ODBs, kind of similar to how a plot overlay allows you to visually do the same thing of adding data together into one spot. It also has a user interface, which is great. The downside is the user interface is a little bit limited, and it excludes the kind of following types of data from the final database. So it doesn't allow you to add in history data, surface data, analytical rigid parts, local coordinate systems on the field data into the new database. So it works for a number of different things, but has a couple kind of small limitations there. But if you want to combine field data from a couple separate ODBs and toss that into a new one, this works very well. I think it also has an XML reader. It has some kind of non-user interface reader that allows you to run the tool as well without having to go through the user interface. It's also on the command line as Abaqus ODB Combine. We also have Abaqus Restart Join. So instead of tossing different regions of a model together, this tosses different steps in analysis together. So it appends an output database file produced by Restart Analysis to the output database produced by the original analysis. So it allows you to generate a single ODB of an original and restart execution. It allows you to get the whole picture in one single database. It adds result data to the existing database, but it has to be the same model data. And it's similar to the Abaqus append command from anybody who has used Abaqus for a little while and remembers the .fil. Another one is the ODB reduction tool. This one actually going from combiners to reducers now. The first reducer to talk about briefly is the ODB reduction tool, which is the ODB splitter built-in plugin. You can go to plugins, ODB reduction if you use that. It allows you to create a new ODB which contains only some of the field or history data. It's nice and quick and easy to generate an ODB with reduced results data. It's very quick to generate that smaller ODB. The downside to this tool is that it requires either a data check or an original input deck to generate a data check in which you can fill data into. And what that means is that since we're running a data check, we have that entire model in there, so we can't reduce any of the model data. So if we've got 20 parts, we end up with the 20 parts still for that second database that we've reduced. Additionally, if you request a field output, it's added for all the included frames. So as an example of that, you can't request displacement in frames 1 and 2, but stress in only frame 1. So there are, it's a nice quick tool. It does work, but it has certain limitations that I found that were a little bit limiting for my taste. We also have the ODB reconstruction tool. This was developed by another previous manager of mine. I've gone through lots of managers. They've all been fantastic, but I've gone through a lot of them. This one generates a simplified ODB for fast visualization. Some of the uses for it is that it can increase your startup and plotting speeds of existing ODBs by you're essentially generating new, simpler ODBs using this tool. You can create smaller ODBs, obviously, out of the original ODB being a reducer, and essentially allows you to hide certain data because you can select only specific outputs for reconstruction. So the upside to this tool is that it's fast to generate. Viewer loads the new ODB in its frames faster because you have the ability to carve out model data actually using this one. So you can specify that, okay, I only want 2 of the 20 instances. It also reduces the model to certain regions. So again, saying reducing the model to 2 instances instead of 20, for instance. The downside to this tool is that there's no user interface, and the model reduction has to be tied to instances or element sets that already exist in the database. The final model data is simplified as well, so there's no assembly data, there's no, say, section categories, and any kind of structural elements, beams or shells, are going to be reduced to membranes and trusses. And again, this can be good if you're looking to just reduce the amount of data completely that's in the database. But again, when you're reducing and simplifying like that, you end up possibly having the hazard of simplifying a little bit too much. But it does give additional small speed boosts. And so for me, when I was working with different customers, these are all great tools. However, a lot of the people would say, okay, none of these really addresses my biggest issue. And that issue is that Viewer works really well on small models. We don't have any issues. It works great. I've got all my tools. It's fantastic. But whenever I get to these really large databases, whenever I hit 10, 20, 50, 100 gigabyte ODB files with 10 million elements in there, Viewer starts struggling. And I want my data. I had to solve this really large model, but I don't really need all of that data today. I might want to store all of that data, but right now I'm just looking at a portion of that. I just care about a couple components of that entire model. And I still have to load this entire database, which is taking a very long time. Step in the new reducer that I built over the last couple of years, and that is the ORB, which previously was called the OEBT. But this is going to be actually available on the Simula learning community. It has been for a number of months at this point, but also there is a current plan to implement this into the Abacus software, and assuming everything goes right, you guys should have a nice little Christmas present. So just a bit of kind of background. There's a lot of data out there, and the one thing that I have seen being here for 5.5 years is that you really never get any smaller on your models. You get bigger. You expect the software to try and keep up and improve and speed up, but you still keep shoving more and more elements at it and requesting more and more outputs. And with that, we have a lot of customers that are running analyses that are really complex systems at this point. Decades ago, we would have had some smaller components, maybe something that had 1,000 elements, couple thousand elements, or something like that. But we've greatly surpassed that at this point in our technological capabilities. So we have customers that are dependent on that almost, and using our tools to run these complex systems of entire sections of aircraft, or drops of entire phones, or doing vibration analysis on whole vehicles. And what that does, it requires a lot of data in the model itself. You have a lot of elements in there. Another thing that people have been doing is requiring results through many time points. So if you think about your field outputs, each field output, each increment is another point in time, and every time point you multiply a single increment data size by, you toss in another one, so it's 2 times, 3 times, 4 times, 5 times as you go up and up and up, and some people get up to 100 or 200 times. Another thing is that analyses are modified and rerun as part of optimizations, design of experiments, operating range workflows. Now, people with a section of an aircraft want to make sure that it works not only whenever you're doing a static loading with half capacity. You need to know that it's not going to break under a 1G turn. It's not going to break whenever it's fully loaded with fuel and passengers and cargo. And you have a number of different conditions which this needs to be run at. So you have a lot of different design considerations. You have manufacturing variability in there. So if your part is a little bit thicker or thinner than you expected it to be, you want to be able to account for that as well. So all of these, again, you multiply however large that model is by however number of frames you have by however many times you run that analysis. And then eventually you may want to pass those model and results downstream to other engineers for further analysis. So if I had a section of a wing, for instance, I might want to toss an individual rib of that wing down to an engineer and say, hey, are we passing limit load? And I don't want to have to give half of the wing down to that engineer, because they don't need millions of elements. They only need 10,000 or something. And so there's a trade-off exists between the analyst time and the model run time and the storage size. if I don't want to spend as much time setting up an analysis, then, I'm not going to be paring down my field output so much. I won't care about that. I'll just run it because I want to get home and I want dinner. But, there's this trade-off between how much data you're producing, how much time an analyst spends to prepare the model, and how long the model is running. And most all of these things are multiplicative in nature. So just a quick summary of that. On the right-hand side, we've got how much data per frame, which is related to the model size. We have how many frames you have of output, and we have how many different analyses you're conducting as well. And that can become a data headache. So the main problem with all of that data is that the models are 1,000 times as big as when the ODB format was first developed. So we were solving, and maybe Nuno can give a better perspective on this, but when the ODB format was first developed, we were working with models that were, hundreds to thousands of elements. And at this point, it's very common for me to work with databases that are millions of elements. It can be cumbersome to open and work with those databases with especially 25 gigabyte files. They can take 5 or more minutes to load, and you can have slow manipulation once they're open. Now, SIM databases and that more modern 3DEXPERIENCE platform architecture addresses some of this, certainly, but we don't have any current tools to easily generically reduce the databases. And, what we want to know, what the question is here is, where does that cause issues with the current workflows? And we'll just go through some of the issues now. So one of those is going to be loading ODB data. Database speed. So whenever you want to load a database, and maybe it's a large model like this one you see here, the typical process that I've seen being on site and working with customers, that I would walk around and say hi. They'd say, oh, I had some question about my model. And I say, okay, do you have it open? They go, no. Okay. So they take a second. All right, we'll go and open it. We'll take a talk about it. So they would go open it, pick whatever they want to open, and then we'd sit there and chat about what the problem was for 5 or 10 minutes while the database opened. We might go and grab a coffee or something like that, and then at some point we finally had that database open. And the point is that loading large models, loading that data can be slow, either because of the model size itself. You might be loading up tons of shells and beams and connector elements and all this other data and all of these node sets and element sets. But you also might be loading up step data as well if you're trying to get to a certain point in your results. But once you have that open, indeed, whenever you have large models, the manipulating results can be a little bit slow in CAE as well, because you have 6 million elements on the screen that we're trying to calculate how to rotate all of those things. So, selections, calculations, post-processing runtime for certain actions can be slow because, again, we're trying to do that for 10 million elements. Downstream analysis, if you want to transfer the database, obviously transferring a 10 gigabyte file over a network can take a while. But if you transfer a 1 gigabyte file over the network, it takes obviously 10 times less. And what I saw working with different customers is that results are often passed through networks. You have either passing it from an HPC to another system or from one user's computer to another user. We're not quite to the centralized repository of databases yet. We are working our way there, but not every company's quite there yet. So for instance, if I have a section of a wing and I have one of the ribs, give an example that I showed a minute ago, I have one of the ribs that needs to be looked at. I can pass that entire section of the wing to the downstream engineer, and he can take 10 minutes to load it. Now, if there was a way that I could pass just the rib to the downstream engineer and he could load that, he or she could load that, they would be able to load up the database real quick, 10 seconds or something instead of 5 minutes, which would be much improvement on the engineering time there. But eventually, they took a look at it and say, oh, we're failing at 1.3 times our limit load. That's not good. So I don't want to have to wait a really long time to pass that data to the engineer downstream and to have them open it up and work with it. Another thing is we have data need to know. So data containment sharing is another issue for customers. or we might have a team of expert analysts run large complex analyses, and a lot of times you only want to share some of those results data outside of the analyst group. And there's no real good way to do that currently in Viewer with ODBs. A lot of times you have results that are analyzed in detail by engineers downstream and or across companies. Now, for instance, if you had a phone, you might have different module level groups, and the same applies to aircraft. You have different module level groups. For a phone, it might be display, printed circuit board, external connections. For an aircraft, it might be side body wing landing gear. But you don't want the module teams necessarily to have access to the full phone, because you don't want your phone leaking to the press before it's out and sent out to customers. And for an aircraft, you have a lot of other companies that are hooking in at different areas. So you might have somebody who's got an engine, and you need to load up that engine onto the wing somewhere or onto the empennage in that image that you see on the bottom. But you may need to work with different groups, or you may need to work across companies, and you don't want them to have access to all of the data that you put into that database. So you have the ability to, with some kind of ODB reducer, you'd be able to either take the whole model and reduce the field data, or you'd have the ability to wipe out material information or sections of the model so that they don't have access to that. And the final one is post-processing support. So one of the main issues is that support can't really directly handle customer models to debug, and that's something I've seen on a monthly basis. Is the customer say, oh, okay, well, it happened a couple weeks ago, actually. Customer says, okay, I have an issue, but you can't look at it. And so as a support person, we go, okay, well, I can maybe look through the 100,000 lines in your message file or your DAT file. It's going to take me a while, and I don't know exactly what I'm looking for, but we can try and do that. And that's very often what happens, is that we try and look on other files for the issue. But more than likely, the proprietary nature of the model and the reason that the customer doesn't want to give it to us is that you have either proprietary model where the geometry itself is proprietary, or the materials are proprietary. And if you had the ability to chunk out just the portion of the model that you're interested in, or wipe the material data, you have a much higher chance of getting approval to send that out to one of us. And what that means is that we can take a much faster look at it. We have the actual data. We just load it up real quick, rotate it on our screen. And if it's a visual thing, or if it's something that we can look at through the API real quick, we can just do that. And it's typically much easier than working with a message or DAT file. So the customer, if they had the ability to break it down, could send it to support. Support could go, oh, yeah, no, it's this. You should probably, you're doing this, you need to be doing this, or this might be a bug or whatever. We can usually identify that fairly quickly if we have an actual model, and that results in a happy customer. So for large models, I'd say that we have all of these issues, and the one thing I'm able to tie all these issues back to is that we have these really large models now. And in 10 years, somebody's going to say that in the exact same manner, and they're going to say, we have really large models now. 10 years ago, they couldn't have done any of this. They were just working with 1 million elements. And I have no qualms with that. I'm sure somebody will be saying that in 10 or 20 years from now. But as of today, as of 2020, the initial ODB storage methodology is a bit outdated. So we used to be solving components. We might have had 100 or 1,000, where we're solving one or a couple individual components. And we were able to distribute that really easily by packaging it up into this ODB file and then loading it up. And it never took an obscenely long amount of time, because we didn't have a massive amount of data that we're sifting through. Now, processor speed and everything else, if you had modern architecture, the computers and the amount of hard drive space that you have today, and if you can take that and use it back then, you wouldn't have any of these issues. You'd just be loading up an ODB file and going. However, with millions of elements, hundreds of output frames, dozens to hundreds of analyses. We're now solving much, much larger data, and we're solving on systems of components now. We've got general context. We've got lots of easier ways to set up large assemblies now and run those in Abacus. And what that results in is a lot of data. And to me, what that kind of says is that we need some sort of distribution model for this data. Instead of having, one car where we could take our box of goods out to whoever, that being the ODB and customer. What we need now, we have much larger databases with 100 instances, large assemblies, and we don't necessarily need the entire assembly for everything that we're doing. We might need to look at one component. We might need to look at a rib or a rib and a couple surrounding elements or something like that. We don't need the whole thing. So what our databases have become are these large warehouses of information. And what we need is to distribute those to kind of smaller regions and use them as we need them. And what that visually represents is on the bottom right, where we have an original result database file, which has some model data, some field data, and history data. And that's what we've requested. And we don't a priori know exactly what we want from our runs, typically because a lot of times we're going either completely blindsided into these analyses or, 90% certain what we're doing, but we still, it's never perfect. And what we actually need from those analyses is that we overcompensate a little bit, which is fine. It just means we end up with more data. But what we actually need from these analysis is some of that model data, maybe a bit of that field data, and some of the history data. And so instead of having this massive database, what we can do is chunk out a smaller portion of that database into a new one and work with that kind of lightweight but still full database. And so to tackle that issue, again, over the last couple of years, I've been working on some tools that are known as field solutions, but field solutions because they're not developed by R&D, but we generate reduced databases to handle all of the things that we talked about earlier. And with that, we have the ODB Reduce Your Builder tool, which again should be coming out quite soon, next few weeks or so. It's got a full user interface. It's deployment ready. I've worked on that over the last 2 years. If you saw the very first slide in this, there was a clock and a little cowboy. And that's because in kind of colloquially have been calling this Project Midnight Cowboy because it's been essentially in my off time. And it's just because I've seen, something that's been frustrating customers and I've wanted to fix it. I want people to go home and, be able to go home at 5 or 6 or whenever they actually want to go home, need to go home and get some food and talk with their family or do whatever they want to. They shouldn't be sitting here waiting on a database to load. So this has a planned implementation as a built-in plugin in the near future. And there's also an alpha stage tool for SIM databases, which is going to be the SIM Reducer Builder tool. It's got no user interface at this point, and but it does have similar kernel functionality to the ORB. So as we move forward, I expect that to be built out to be utilized for SIM databases as well. So an example workflow, and we'll get to a demo real quick here in a second, is that, okay, I've got a model. I don't need the entire model. I only want a section of it. I only want a couple instances out of my 20, or I only want this particular region that I'm interested in. And so I want to carve out that region of the model. I can use the viewport to put whatever I want into the current viewport. I can use the user interface to select what features I want and run the execution on the ORB. And once that's done, we end up with some data output. And so if you take a look here, there's, I don't know if you can see the mouse, but on the 2 trees in the top right, we have 8 frames in the first step and 2 in the second step. And we don't need all of that data, so we end up with 1 frame in the first step and 1 frame in the second step after the extraction. I've also tossed out some of the node sets that we don't care about and some of the element sets. If we have certain material data, which we'll talk about in a second, I have the ability to wipe material containers or completely not include them, but we'll talk about that in a second. But in the end, we do a reduction. We reduce the model data, we reduce the field data, We can say whether we want the history output or not as well. And what that means is that we can end up going from an 8 megabyte database to an 800 kilobyte database. And we can run the tool, and the tool runs in a little over 3 seconds to do this. So I'll boot up a demo, and we can see that in action. There we go. All right, should be able to see that. So to access, we go to plugins, ORB, and that might be OBT if you're still using the SLC version. But what it pulls up is this user interface, and we can run this no GUI. We'll talk about that in a minute, but you can run this without the user interface. We have the master controls over here on the left, so if we can turn on and off our kind of major groupings over here. So sets includes node, element, surface sets, properties, sections, materials, profiles, datums for all of your datums. Then we've got our steps and frames, which are step and frame containers. We also have our field outputs, which is stress, strain, etc. And then we have our history outputs as well. And so if we don't want history outputs, we can just uncheck that box, for instance. The default method of what region of the model you're going to carry over to the new database is by whatever is currently displayed. We have a number of other options as well. However, the currently displayed is kind of our standard. And with the currently displayed, you can use the create display group dialog box and use this to kind of filter anything you want. For instance, if I wanted only elements above a certain stress value, I can change it to displacement or whatever in here, but I can say, okay, only extract out the elements, put those on the viewport, and then eventually we'll extract those. But say, put only elements above 200 MPa on the viewport. We can also select specific part instances, or kind of my favorite for demonstration purposes at least, is that we can just carve out a region of the model. And by default, we take whatever is currently displayed on that viewport. Sets, we can either take all of the node sets, none of the node sets by unchecking that box, so we can select specific node sets to keep. Same thing with element sets and surface sets. And then properties, you can select, do the same thing with sections, materials, and profiles. However, instead of picking certain sets to keep, instead for sections and materials, we can nullify the material. So we can wipe the extended data. So the elasticity and plasticity data, if we don't want other people to access it, but we still need the containers for the materials, we can nullify specific materials or nullify all of them, or we can keep the full data, which is the default. Or if we don't want even the names of the materials, we don't want anything to do with materials making it into the new database, we can uncheck that. Now by default, any data that's tied into elements or nodes somehow, which sections, materials, profiles certainly are, and node sets, element sets, surface sets are, anything that's not extracted out to the new database as far as the mesh goes. So if I extract a region of the model and I have materials which are not in that region of the model, those materials don't make it into the new database. So we're down selecting as we go with everything. By default, steps and frames match your field output requests. And so in the field outputs, well, we can also say, okay, I only care about the last frame in the first step and then the last frame in the second step. And that reduces your field selections to only those two and make it a little bit simpler. But let's say that, okay, I've got, I need to know my strains and my stress and displacement at the end of the first step because that's going to be important to me. So we'll update that. And at the end of the analysis, I want to see if anything's in contact. I want my strains. I'll take my reaction forces and my stress and displacement. And so we'll update that as well. And so we've got a nice little preview down here at the bottom that tells us what we're going to extract. And once we're ready to go, we can hit generate ODB. And that'll run. And again, just a couple seconds there, and we end up with our final database. And this is doing that reduction that's probably about an order of magnitude from that 8 megabytes to 800 kilobytes. Now, we also have the ability to, try not to take too long because we've only got a few minutes. We can look into the materials. I believe I reduced the titanium out, but you also have a printout down here of everything that we've done with that extraction. So it tells you all the sections, all of the materials, for instance. So you see the aluminum, we added density, elastic, and plastic because we requested all the default information for that. We requested to nullify titanium. So it says titanium, but there's no detailed data inside there. And so we can check that just by digging into the API, by going into materials, datum, and we can go and print that. And so you see the original database has density, it has elastic, plastic, etc. But if we go to the new database, none of that made it in there. So this tool allows you to create new reduced databases and allows you to do it quickly and gives a very high level of control over what goes into new database. Just real quick comment on NoGUI. You can run it NoGUI. This is the script to run it NoGUI. It's like 10 lines without comments. You just tell it where the tool is. You give it, the tool uses a JSON file, uses a parameter file to do the extraction. So you tell it where that parameter file is. And you can save and load parameter files from the actual the actual tool itself by going in here and saying save settings or load settings, and that'll save a file in there for you. So you can use that downstream if you want to run it NoGUI. You can manipulate that or do whatever you need to. So you give it the path to that parameter file, you give it the path to ODB and the tool path. You just load up the tool path into the system path. And then you say from OEBT kernel, import extract file. I think the SLC says something different, but please go with this. From OEBT kernel, we renamed that file, so use this. And then you just call extract file, and that's it. And that'll run it, it'll give you a new database. We've been working on improvements to the ORB as the months and years have gone by. So this was probably a year ago where we had this kind of baseline over. This is a large aerospace model, about 6 million nodes and elements, and it used to take about 3,000 seconds. I put in incremental improvements to the tool, so we've dropped and dropped and dropped as far as run speed, as far as runtime goes, and we've dropped from about 3,000 to 900 seconds, and we expect there to be further performance improvements as we go along, but it's quite good at this point. And we've reduced the memory required from about 12 gigabytes to 6 gigabytes, or 6.5, something like that. So we do have improvements that continually go into this tool. The right-hand side is just kind of a change log, just to show you that there's lots and lots of improvements that go into it. And just as kind of an example to sort of wrap us up here, we have the ability to repackage results data. So we have the ORB, which you can use to reduce a database from something large to something much smaller, and you can change the name of the new output file on the bottom left as I did there. So what I've done is extracted one of the plates out of our lap joint model to one database. I'll toss the other plate into the viewport, rename that to P2, and extract that out to a separate output database. And once I have these two, I have some split data now in separate databases, and what I can do actually is I can combine these ODBs if I want into a single ODB. I can say, okay, give me all the stuff. These are my two databases. Run it, and now I've got one database with these two laps in there. So that's an example of breaking databases down and rebuilding them back up, which is a nice little kind of story, I think, in my mind. We're showing something with two instances. Obviously, this applies to any database. You can have 30 instances. It can be aerospace. It can be transportation. It can be high tech. Whatever you want. It's as long as it's an ODB file, you should be able to do it. And so last kind of page here is you want the right data in the right place at the right time. ODB manipulation tools exist to convert, break down, and build up your results. We have APIs that allow you to do any kind of additional manipulation needs, and you don't want to overwhelm yourself with your resources. Overwhelm yourself with data if you can help it. So you don't want to, the same way that you don't want piles of papers on your desk, you don't want piles of data in your ODBs if you can help it. You know, if you have a smaller ODB, it's much easier to work with. You can focus on your tasks, and it's not going to take you 10 minutes just to find the correct paper to work on. And that's it.